Okay, this is my second go at recording because the tablet kind of disappeared on me midway through just now. So hopefully that doesn't happen again. So new problem solving session. This is the requests that we got. I'm trying a new layout where you can see the problem side by side with the tablet. If it makes the content on the tablet like too small to view on YouTube, please let me know and I can go back to the other way. But jumping right into the questions, the first is a request to talk about 10.2, question 5. That's this one right here. It's one of those limit problems. And I think by this point in the web work, you would have already seen limits, but this might be the first one we use L'Hopital on, and this J-hat component of the top one was giving people a lot of trouble. So I'm going to talk about this more broadly first, just how we do this type of problem, and then more specifically how we deal with that J-hat component. So the general approach is going to be to, first of all, take our limits component-wise. That means that we're going to treat I hat, J hat, and K hat separately. And then as necessary to take those three different components of derivative, we might need to use L'Hopital's rule. So that's going to take us back to what you would have learned in Calc 1, I think. But the approach is that we're going to take derivatives of numerator and denominator. And then take the limit again. And we do this when we have like a limit where we get 0 over 0 or infinity over infinity. And then I guess just sort of one thing to be careful about or to note is that because we treat I hat, J hat, and K hat separately, when you do L'Hopital's rule, you do it on like a component by component basis. So even if you need to use L'Hopital's rule in this component first here, that doesn't necessarily mean that you need to take derivatives in the third component here. So I'm writing that as L'Hopital only applies to each component, but just that was a question that I heard a bit in class. And then the specific issue people are having here is, actually, yeah, I can go kind of slow. We've got 4 problems to get through. So, for example, this first component, limit as t goes to 0 of sine of 3t over sine of t I hat. So let's say that I'm taking this limit and I've decided to go component-wise and I've gotten to this first component. Then I'm going to erase the I hat just so that I can actually fill in the next space. But if I tried to figure this out, I would run into the problem that sine of 0 is 0, so I would have 0 over 0, which is undefined. So instead, I'm going to go ahead and apply L'Hopital's rule, and it's going to be the same as the derivative of the top over the derivative of the bottom, taking that limit as t goes to 0. So that's going to give me limit as t goes to 0 of 3 cosine of 3t over cosine of 3t. And that one I can go ahead and evaluate directly because cosine of 0 is 1, so I would just get 3 for my answer there in the I hat component. But more specifically, what's giving a lot of people trouble is when we go to do natural log of sine of 3t over natural log of tangent of 3t. Because once you start taking L'Hopital's rule, everything becomes kind of a mess. And I'm not going to do that because it's a lot of algebra. I'll maybe leave some space and come back to it if I have time at the end. But I sent an email out this week. Sorry, not this week anymore, last week, after this was assigned, kind of explaining how to do this problem. And I'm just going to say here the same tips that I gave you. Basically, we're just going to use trig rules to simplify it. So you're going to want to take a first L'Hopital's rule, and then you're going to want to use trig properties to simplify it. So use tangent of t is equal to sine of t over cosine of t. Use secant of t is equal to 1 over cosine of t. And then also use the, I think, double angle formula, which is cosine of t sine of t is equal to a half sine of 2t. So after you make those substitutions, you just simplify your fraction. It should be a ratio of simple trig functions. By simple, I mean like sine, cosine, and tangent. And then just take a second L'Hopital rule. Which will be a lot easier because it's simple trig functions. And then at that point, you'll have your answer. So that's how you do that one. These down below, you can also do with L'Hopital or with factoring, whichever you prefer. And kind of as a hint, if you're not really sure how to factor what's on top, look at the factors in the bottom, or note that the thing that tends to be breaking your limits is t goes to 3. So usually you want to be able to factor out a t minus 3. So you're going to check for those factors in the numerator to cancel them out with the denominator. Yeah, I think that's most of what's difficult here. Oh, I guess for this last term, the k hat, the natural log of 0 is undefined, but you're multiplying by 0, so kind of like even though, let's plot natural log, even though kind of as you approach 0 you're going down and you're getting like negative infinity, it's being bounded back towards 0 because even a very, very large number multiplied by 0 is still going to stay 0. So that last component you don't have to worry about L'Hopital on. So hopefully that covered that question. like I said, we'll go back and do some of these in more detail. Maybe that gross trig one if I have time at the end. So let's see, I'm having trouble understanding what question 7 is asking for. So homework 10.4, question 7. So this one is asking us to find the x-coordinate of the point of maximum curvature. And they give that coordinate a name, x0, so that they can ask for it later. And it's requested on the curve y equal 3e to the 5x. And then also to find the maximum curvature kappa evaluated at that x0. So if you're unsure about how to start this, first things first, we're going to need curvature. And this is one that's going to be easier with that one-dimensional curvature formula. Oh, I already did equal. That I threw up on the board in class. Like that. Oh, whoops. Oh, you probably want to make those flat lines. So unlike the one that's like r cross or r prime cross r double prime, this one is written already in the form y a function of x. So here y equals 3e to the 5x is our f of x. So we would, sorry, I don't know what I'm doing to this thing today. So we would take f double prime, or I guess we would go in order of derivatives. We would take f prime, which is just y prime, so derivative of that exponential, it's going to be, 5 comes out front times 3 e to the 5x. And f double prime is going to be just a second derivative of that y. Which I think is 75 e to the 5x, but I'm not 100% sure about that multiplication. And now everything that we need to make kappa work is defined. So we could go ahead and put up top the second derivative and down below the first derivative. And we can ignore those absolute value bars because the components are positive. Exponential returns positive numbers. And then at this point, we have curvature in terms of x. So up top, you're just going to have this 75 e to the 5x divided by 1 plus 15 e to the 5x to the power of 3 halves. And so for any given x value, you could evaluate kappa. So you could plug in any x to get curvature at that point. What we want is the maximum curvature. And so this is the part where it gets a little bit tricky. You should recall, I think from your Calc 1 class, and you would have learned that maximizing a function is the same as checking when its derivative is 0 and checking that that value either passes the second derivative test or is just bigger than the things around it. So we're going to take the derivative with respect to x of that kappa, and then we're going to set it equal to 0. So you're going to get 0 is equal to that f double prime of x divided by that 1 plus f prime of x to the power of 3 halves, the derivative of that. And that derivative is kind of messy because of this term down here. But it is just a, I'm so sorry if you heard that. My dog is sleeping and she just is snoring really weird. Okay, so it's a gross derivative, but it's just a quotient rule, or if you want to think about this as like a product of something with a negative power, then it's a product rule. So you can also think about it as times 1 plus f prime of x to the power of negative 3 halves. Sometimes that's a little bit easier for people. And then you just solve for the x0 that gets you this value at 0. So you're just solving for x the way I've written it, but WebWork calls it x0. And then at the end, you're going to plug that back into kappa to get the second part of the answer. So hopefully that answers the question of what they're asking for. And then the other question here is question 2 in 10.4. So that's this one about unit tangent vectors and principal unit normal vectors. And so this one is just sort of like a straightforward application of formulas. So we're given r of t, we compute r prime of t with component wise derivatives. So just like the I hat component, take your derivative, you're going to need a power rule, then your j hat component, same thing, and then your k hat component is the easiest one. And then we're going to compute our magnitude, which if you've forgotten the formula is going to, I made that way too long. If you've forgotten the formula, is just going to be like the, yeah, I can use xyz here. The x component, that's the I hat part squared, plus the y component, that's the j hat part squared, plus the z component squared, that's what's on the k hat. I don't actually want to leave that there because I don't want you to think that that's part of your answer. Figure that out closer to when it happens. So yeah, that's how you compute the magnitude for the second part. So you're doing the magnitude of the derivative. Please don't go back to the first capital R. You're doing this to r prime. And then just a formula that we were given in our notes is that the tangent vector points in the direction of r prime of t. And so to make it a unit tangent vector, we divide by its magnitude. That's something we learned in the first section of class. So you're just going to take what you got in the first box divided by what you got in the second box, and that's your answer for the third box. N gets a little bit trickier just because you're doing the exact same thing. So you're going to take the derivative now of that tangent vector, and then you're going to have to divide by the magnitude of that tangent vector. And the only reason this is tricky is just because the magnitude in the denominator again makes this like a quotient rule or product rule with negative exponents problem, so that derivative is just kind of tough to take. But you can just directly compute it for each component, and then at the end calculate the magnitude and divide by it. And then just a warning, you don't need to simplify it. WebWork is going to simplify your answer and figure out if it's correct. And on an exam, for example, if you go to the effort of simplifying something, you're like wasting time you could spend on other problems, and you're increasing the chance that you turn a right answer into a wrong one. So once you get whatever you have for n, just leave it there. But if you remember, sine squared of, for example, minus 2t. If you remember that sine squared plus cosine squared is equal to 1, then in the middle step right here, I'm going to indicate that with a little star as you move from there to there. And then just use that substitution where you see sine squared plus cosine squared, and maybe you have to rearrange things a little to pull out like a common term. But then just use that substitution of 1 to make your derivative simpler. If you don't take that hint, you will still get the right answer. It's just that computing that derivative becomes a lot more difficult. So I do recommend making that substitution between the third box and the fourth box, just to make your life a little bit easier. But that's all that you would need to answer that question, I think. Is there anything else? Nope. Okay. I opened these in advance, but I always want to make sure I'm not missing something. And then the last request is for 10.2 question 6. So that's this one right here. And so we're asked to find the position vector capital R of t when we're given the velocity v of t and the initial position vector r of 0. And so our strategy here is going to be to remember that position should be the integral of velocity. Like we learned that acceleration is the derivative of velocity, velocity is the derivative of position. It goes in reverse. If we want to find position and we're given velocity, we just have to integrate it. So we're just going to integrate v of t component-wise. And this one doesn't have any weird integrals. I thought there was one where you had to do a u sub. Messed up. I guess I was thinking about a different homework. Anyhow, so this integral should be pretty straightforward. You're just going to do it component-wise, do the I hat, j hat, and k hat separately. And then don't forget that whenever you integrate things, you're supposed to add on an unknown constant. So when you take your antiderivative of little f dx, you get some capital F, a function of x, but then there's also an unknown constant on the end that we don't necessarily know. And then you're going to use R of 0 to find C. What I mean by that is that you're going to plug in t equals 0 to r of t, the integral of v dt. And then you're just going to ask yourself, what does c need to be in order to match r of 0? And then you put in your final answer that has both the parts that depend on t and the unknown constants. So I'm going to show you what I mean, for example, just looking at the I hat component. So here, I have in the I hat component, it's 2t plus 3 I hat. So then my r in the I hat component would be 2t plus 3 dt I hat. So I'm just integrating. That's going to give me t squared plus 3t for the two components that I see, but then there's also an unknown constant. And maybe we call it C1 because when you do the j hat and k hat components, you'll also get unknown constants. But if I plug in 0 here, I would get 0 squared plus 3 times 0 plus C1 I hat, or just C1 I hat. But I'm also told at the start that r of 0 has to have this specific value in the I hat component. So it has to be minus 3. That means that my C1 has to be minus 3. So I would go ahead and sort of like right here where I have that C1, I would say, okay, that had to be minus 3 to start. Now if I go back and I plug in 0, I would get 0 plus 0 minus 3 when time equals 0, and that perfectly matches that when time equals 0, my r should return negative 3. And so then I would just put this in my answer. I would say t squared plus 3t minus 3 I hat, and continue the same for the j hat and the k hat. A problem that I was seeing on this one is that, oops, that's not how you spell does. So something that I was seeing people do is maybe after the first time, or just by randomly trying things in WebWork, you would think that the solution is to take the integral of v and then add on whatever r of 0 is. So for my I hat component, that would work. I actually get minus 3 for my constant, and it's the same as what's in r0. But that's only because when I plug in t equals 0 to r here, I got 0. So that only works if your integral evaluated at 0 is 0. But for example, when you get to that second component and if you have a cosine in it, then it's no longer going to work. So you're going to have the problem that the unknown constant here is incorrect. You do have to solve for it algebraically, like I was describing here. And I'm going to go back to the forum, make sure I got everything. I think this is just a repeat of that one. Yes. Okay. So with 20 minutes, I can try to go into more detail on things. I guess I'll start with this one and go backwards. So when I say you need to solve this algebraically, what I mean is for our j hat component, if I did my integral of 3 sine 3t dt, I check the integral of sine on my phone because I can never remember which one has a negative. Okay. That's going to be negative cosine of 3t plus a constant. I guess I'll call that C2. So when I evaluate it at 0, I get negative cosine of 3 times 0 plus C2, which is just negative 1 plus C2. But I also know that R of 0, sorry, all this is about j hat, just so you know. But I also know R of 0 should be 3 there. So I need to have negative 1 plus C2 is equal to 3, or C2 is equal to 4. So then in my j hat component, I would have negative cosine 3t plus 4 j hat. And I would just add that on here. The way I'm working this out component by component, you can do. You can also do it kind of all in a line. So something that some people like to do was to do like r is equal to the integral of v dt plus c, a vector, and then they set that equal to negative 3, 3, negative 2, also a vector, and did, plugging in 0, so kind of like they plugged in t equals 0 there, and then they just did vector-wise algebra to solve for that c, and you can even write your answer as the two components separately. That's a valid way to do this. I just showed it this component-wise way, first of all, because I thought I would only have time to show one component, and second of all, just because it's all the same and you work through them more or less independently. But whatever way is easier for you is fine. So rolling back some more, let's see if there's anything more I could say about this one. Maybe I'll do more detail on one of every person's problem first. And I think this maximum one is a little bit harder. So let's go ahead and do more details there first. So I'm going to go ahead and delete all this that I did and go ahead and plug right in the functions, because I took those derivatives on the other page. So I had 75 and 15. So this is the way that I prefer to take the derivatives as a power rule. Here's going to be my f, here's going to be my g. Oops. And that 0 is for the derivative. I'm using a sloppy notation here for getting that d dx. And I should be more careful about that. So my answer is just going to be f prime g plus g prime f, where f prime is going to be, wow, already I don't want to do that. I'm going to change it back to this, 5 times 5 times 15 e to the 5x. So that 70 was 5 times 15, and another 5 comes out front. And I left it that way in case some of those numbers cancel out later. And then my g prime is going to need a power rule first. So like this -3/2 comes out front. And then I subtract 1 from my current power, and it becomes -5/2. And then it also needs a chain rule because what's inside wasn't just like x, it's a function of x. And so that derivative is going to be 5 times 15 e to the 5x. All right, so I'm going to go ahead and just plug those things in. So I have 5 times 5 times 15 e to the 5x for my f prime. My g is 1 plus 15 e to the 5x to the -3/2 plus my g prime is -3/2, 1 plus 15 e to the 5x to the -5/2, 5 times 15 e to the 5x times f, which is that 5 times 15 e to the 5x. This is a lot, but it's okay. Let's pull out things that are the same. So 5 times 5 times 15 e to the 5x is in both terms, like that and like that. And so is 1 plus 15 e to the 5x to the, which one do I want to do out front? Do that one. To the -3/2. So this -5/2 is just -3/2 times -2/2. So what I'm going to get is that's 1, because I used both terms in the first, minus 3/2, 1 plus 15 e to the 5x to the -1, 15 e to the 5x. And that factoring out that -1 is just because -5/2 is -3/2 minus 2/2. So it's like a product of -3/2 and -1. Then, oh shoot, before I did this, I said that I was going to check if anybody posted anything else. No, okay, phew. And I'm going to be quiet for a minute while I go find a charger too. Sorry about this.